like Phil said, I'm Shane Snyder at Argonne National Labs. And I work I spend a lot of time working on a tool called Darshan, which Phil has already referenced a bit in the introductory materials, but it's basically a tool that can help you start learning about the I/O behavior of your application. So as users of HPC facilities, I/O is kind of one of those pain point areas that no one is super fired up about dealing with, but it's something that you will have to probably contend with in your day-to-day job, whether you're working directly with I/O or you're working in applications or workflows. It's something that you'll probably have to deal with at some point. And in which case it makes a lot of sense to have a tool available to answer some important questions for you that give you a better context of what your I/O behavior is like and how it could potentially be improved. So some example questions that you might ask just to kind of as a starting point to get your bearings on your particular I/O workload is first off, how much time you're spent reading and writing files. That's just like a very basic concept, but compared to how long your application's running, how much time were you actually spent doing I/O. So if you're running for 12 hours and you spent 15 seconds doing I/O, then maybe you've got more important things to worry about. Another thing is, how does your I/O performance scale up as you add or grow or shrink your job? That's also important. It's possible you could design a software system or a storage system or inherent one that you're tasked with maintaining, and you notice that it performs really well at some scales, but as soon as you increase beyond some scale, it just kind of blows up. And you may not completely understand that and need more data to kind of understand why. Something that Phil touched on, I think a decent amount in his presentation was this problem of performance portability across different systems. So you may have like a super optimized I/O workload on one system that performs great. So for instance, Theta at Argonne, and then you try and port it to somewhere that's a little bit different, like Summit at the Oak Ridge computing facility, and notice like a huge drop in performance or something like that. Those types of things are pretty common and something that you constantly kind of have to deal with as you're trying to port your software to new places. And lastly, how can you prioritize I/O tuning to get the most bang for your buck? So a lot of scientific applications are obviously really complex, and they're not accessing a single file necessarily, or maybe not even a single file system. So there's a lot of data to kind of dig through. So having a tool that can kind of help orient what you should focus on, perhaps parts of the files that you're accessing in your workload that are really poorly performing, that can kind of serve as a good starting point for getting huge improvements out of your I/O performance. So what we generally recommend is a tool that we work on called Darshan as a starting point. And this talk will just kind of give you some brief introductory concepts on Darshan, like what it is, how you use it on different systems, and what you can generally learn from it. And we'll see more on it throughout the day, but this is just kind of like a primer, basically. So what is Darshan? It's just basically a scalable HPC I/O characterization tool. So for every job you run on a particular HPC system, Darshan can capture like a really condensed view of application I/O behavior. And it does so with really low overheads, which makes it attractive for using basically full time. So to kind of hit on some of the key features that make it pretty popular across HPC facilities is one, that it's widely available. So it's deployed at a ton of different supercomputing sites. This includes ALCF, OLCF, and NERSC, which you guys are probably all familiar with or use regularly or will do so. So it's usually just kind of already available for you on these systems without too much additional work. Beyond that, it's really easy to use. So you don't have to make any changes to your code or your development process. Generally, what you would have to do is just recompile your application in some cases, but for shared libraries, it's possible you could just insert the instrumentation completely at runtime with basically no modifications to any of your software or build process. And again, the performance overheads are really negligible. So applications, it's not something they're really going to notice, and something that can, run in the background and capture data for us without perturbing applications too much, which is great. And lastly, it produces a summary of IO activity for each job that you run. So this, this summary includes different histograms, timers, counters, all kinds of statistical data for every file that your application accessed. And this is, just a really great starting point for kind of orienting yourself to what your application is doing from an IO perspective, and kind of, general performance to different files and file systems and things like that. So how Darshan works, it traditionally was designed for MPI applications. And that's, most of our deployments at HPC facilities are based on, integrations with MPI compilers and stuff like that. So that's traditionally how it's been used. I will mention that we do allow instrumentation of non-MPI applications, which I'll cover more in my talk this afternoon. But we're excited about that as it kind of extends Darshan into new contexts that are becoming more popular in HPC. So we're seeing an influx of non-MPI systems and things like that the users are really excited about using, and Darshan can be used in these contexts too, and we'll see more about that later. But basically, what it does is it just inserts lightweight instrumentation into your program directly, either at compile time or at runtime, as I mentioned earlier. And so what it does is it intercepts all the different function calls, IO function calls your application might make, and it captures a bunch of statistics and stores those in like a bounded memory at each rank. And so it does that throughout runtime, just capturing these statistics as you make IO calls. And then what happens is whenever your application exits, Darshan will kind of aggregate all those statistics together. It'll compress them and write them out to a single summary file, summary log file for your job. So you get one of those logs for every single MPI run or job run and invocation that you use. And then Darshan also provides some command line tools you can do to interpret statistics and inspect log files and things like that. So we'll go through some examples on how to use Darshan on Theta in the following slides. There's a GitHub repo that includes some hands-on exercises and examples that we've got for this Darshan talk that you can have a look at. Those are pretty much geared towards Theta, but shouldn't take too much tinkering to make work on other systems. The key difference for other systems beyond Theta is mostly just where Darshan's storing its log files, and whether different analysis utilities are actually available or usable on these systems. In some cases, it's ultimately easier just to copy log files from some systems to like your laptop or somewhere else to do the analysis on. So that's something you might want to keep in mind. But we'll briefly cover the differences between Theta and other systems after this, just to give you a feel for what you would have to do differently somewhere else. So the first step on Theta is just to make sure that Darshan is loaded. So if you log on, you should be able to use this module list command to show you which software modules are already on and enabled. And you can see here that Darshan version 330 is already there and loaded. So you should be able to just proceed at this point and start compiling your application and whatnot. But if not, you can manually load Darshan like I do here at the bottom, and then it'll insert it into your environment properly so that it can be used. The next step is exceedingly simple. So you just compile and run your application. So on Theta, you do have to recompile to get Darshan instrumentation, and that's pretty much it. So everything else kind of happens transparently in the background when linking happens. The only caveat worth mentioning, which generally isn't a huge problem, but you have to make sure that your application is calling MPI initialize and MPI finalize to generate your log. Darshan initializes its library at MPI init time, and at MPI finalize time is where it kind of generates the log and collects all the data and stuff like that. So if your application bypasses those calls, Darshan never really gets a chance to get in the loop. To find your log files after your application runs, you'll need to look in a central location on the system to find your data. So all Darshan log files go in a central directory. On newer Darshan versions, you can use this command called darshan config with the log path option to find what the central directory is. And you can see I've ran it here, and you can see that there's stored on this Lustre volume and this darshan theta directory. You can cd to that, and then you can see further there's the directory is broken down into dates. So I'm changing directories to the 2021 August 4th directory where I did some runs. And then I can ls and grep for my username to see which logs are here. And you can see a ton of different logs that I generated on this day. And you can see the logs kind of all have a consistent format, starting off with your username, and then next your executable name, and then your job ID. What you can do after this is find your log file of interest, and generally what you want to do is copy that somewhere else where you can start to analyze it. So next we'll move on to the Darshan job summary tool. So what you can do is in this hands-on directory, there is a setup script for Theta specifically that loads the necessary modules to run our job summary tool. So after you've got that loaded, what you can do is just invoke the Darshan job summary script directly on the log file of interest. And then you can see what happens is it results in a output PDF that has the same name as the log file with the PDF on the end of it. And that represents the job summary that's generated by this particular tool. And we'll walk through that quickly in a couple of slides. But just wanted to mention for other systems how you would use Darshan. For Cori and Summit, the Darshan's already automatically enabled, so you shouldn't need to do anything, much like Theta. On Ascent, you would need to manually load Darshan. It's not loaded by default there. And you can see on these other systems, there's different locations for the log directory. So you'll need to look into the appropriate place for your log files on each one. So for a Darshan job summary tool, this is what generates the PDF that contains a bunch of different graphs and tables and performance estimates for your application. And we'll kind of cover these quickly in the next few slides just to give you an idea of what's there. So the PDF header contains some high-level job information. So the very top is your executable name and the job date. So I ran this benchmark called IOR on August 2nd. Then next you have some job information like the job ID, number of processes that were used in a total runtime. And we also have some IO performance estimates we're able to provide at different layers. So you can see here at the MPIO layer, which we'll cover in one of the next talks, you can see a higher performance to a larger like 8 gig file. And there's also a standard IO layer, which is using like operations like fopen, fclose, and so forward to read a much smaller file, like less than a megabyte. And you can see here just from this performance estimates, the disparity between the big bulk application IO that's issued through MPIO layer, which gets really good performance and it's a lot of data, versus the smaller config file that's accessed at standard IO gets much less performance because it's not accessing as much data. As far as different plots that are available, we'll focus on a few of them. So the one on the left side here is this average IO cost per process graph. It just shows you for different IO APIs how much time is being spent in different operations like read, write, or metadata, or just application compute time. And you can see, for instance, here, POSIX and MPIO, there's a ton of time being spent doing write operations. This may not be a good thing if you guys saw this for your applications. You would not expect it to be dominated by IO. In this case, it's a benchmark, an IO benchmark, so it does seem sensible. But one thing you could look for is just, if you're spending a lot of time relative to application runtime on these different IO calls, that might be a good idea of whether optimization is useful for you. On the right side, we have total operation counts across different interfaces. So you can see the total number of reads, writes, and different metadata calls. What you'll want to keep an eye out for here is just like really large numbers of different IO or metadata calls that could maybe be optimized by reducing the number of those, as that can kind of really overload your metadata servers and could lead to poor IO performance. Next, there's this on the left side, this IO access histograms. And this is for the MPIO interface. But basically what it does is it shows you the range or the distribution of different accesses issued to your files. And one thing you can keep an eye out for here is whether there's lots of small accesses, like say, on the order of tens of kilobytes or less. Those are notoriously low performing on parallel file systems and things like that. So it's something that you generally don't want to issue a ton of. So you'd much rather have like larger, access sizes represented in these types of graphs. So that's another thing you could look for. And the other thing is this table on the right, just kind of giving you an idea of how many different files were accessed and read-only versus write-only or read-write modes, and also kind of like the average sizes of each of those types of files can just give you an idea of how many files you've accessed and, and things like that from Darshan's perspective. We can also provide general time bounds for read and write activity for independent files, which I have illustrated here, and also shared files. So it can give you an idea of when read and write patterns are happening. In this case, you can see a write phase on the bottom, followed by a read phase across all processes. So yeah, this is kind of quick, but basically, this is, I guess, this is just kind of like a starting point. So, keep that in mind that, the Darshan job summary tool is just kind of meant to give you some context and some clues to what might be happening with your IO. But it's always good to remember you can contact your site support team for help. In which case you can use this Darshan job summary tool as a good discussion starter. So you can use this if you have particular questions about it, or even if you're just not even really sure where to start. This would be a good kind of way to frame the discussion with your site support staff. And so this is only a portion of the Darshan job summary output. So have a closer look and see if anything stands out to you, and let us know if you have any questions. But this is kind of like where a lot of Darshan users kind of start with their IO analysis. There's also something we haven't shown here, which is a tool called Darshan Parser, which literally just dumps out all of the counters and statistics and whatnot that Darshan has captured for every file that your application accesses. This tends to be somewhat overwhelming for users unless you know exactly what you're looking for. It's just kind of like a mountain of information. So not necessarily the greatest starting point, but if you have like an idea of what you're looking for and want to do some custom analysis, that would be kind of your approach there, is to use the output from Darshan Parser.
Hey, Shane.
Yeah.
There's a question from Slack. I answered it briefly, but you may want to speak to it for a minute.
Okay.
Someone wanted to know if Darshan could be installed on a non-HPC system, like a workstation that doesn't have a parallel file system.
Yeah, absolutely. So that's actually where I tend to do a lot of my development work. It's a lot easier for me to do some hacking on Darshan on my laptop and then to run it directly there, in which case, I have MPI compilers there where I can use the MPI enabled version of Darshan, but I can also use the non-MPI version if I wanted to look at something that doesn't use MPI. But it's really straightforward to get working on your laptop. And from my perspective, when doing development style stuff, it's a lot easier to do testing and prototyping there than waiting for a job to be submitted on the HPC system. So definitely, I think a lot of us use Darshan just on our laptops, just if it makes sense.
Then another question is Darshan compatible with the various MPI threading modes if you use thread multiple or sequential or any of those modes?
Yeah, so Darshan should be fine with those. I guess Darshan does struggle a little bit with true threading. So like if you have multiple threads in a single process trying to issue IO at the same time, then Darshan doesn't use like locking and stuff like that for some of its counters and statistics. So threading could make some of the numbers look a little bit off. So for instance, like IO timing, if a bunch of threads are reading something at the same exact time, then those are all going to be kind of counted, aggregated together, and it could make things look longer than your application runtime or something like that. But there's no like incompatibility with those things per se. Okay.
Right, thanks.
Yeah. I'll move on and just give you guys some tips and tricks that you can use to get a little bit.
Sorry, one more that may be easier if you flip back to the slide that had the time span.
Yeah, right here.
Christopher is looking at the Hello World example from the hands-on, and he has a time span that goes from 1 second to 12 seconds, but the cumulative time is less than 1/10 of a second. So he's wondering why that doesn't match. So that may be
Right.
something.
Okay. Yeah, I don't think I did a great job of covering that. So one of the downfalls of Darshan's lightweight instrumentation, and we'll kind of get to the opposite end of this here in a second, but we only capture the bounds of like read and write activity. So we don't capture every single operation and the time bounds of each one. We just kind of have this aggregate like a per process view. So really all we capture is like when a file was first read and when it was last read. So we can see like the complete duration, but we don't know like necessarily how intense the read and write activity was within those bounds. So it's kind of it's useful in some cases, and it's not necessarily as useful if you have like a lot of different IO phases. In which case, you know, you'll see this behavior like you're describing, where there isn't a ton of IO activity issued per se, but like there's big gaps in between when the first one was issued and the last one was issued, and Darshan can't exactly tell you in its default mode where the majority of that happened within that time bound.
Yeah, so maybe one way to think of it is it can't tell you how sparse or dense in time the IO accesses are. There could have been a few sprinkled between 1 second and 12 seconds, or it could have been continuous.
Right.
It sounds like in your case, there's just a sprinkling of IO in that time range.
Right. So this next part of the presentation, we'll just cover a couple of tips and tricks for getting more detailed information, and I think it kind of lends itself to that question. I'll get there in a second. But first thing you could consider trying is I mentioned there's these 3 panes for these read and write activities we were just discussing, and the example we just looked at was the top 2 panes, which are for independent file accesses. So these are for files that are not shared across all processes. You can see in this particular example, there aren't any non-shared files. So those 2 panes are empty. Instead, you have at the bottom, read and write activity all on 1 pane for all shared files accessed by the application. And in this case, you can see kind of similar to what the user mentioned a second ago, is that there's not a ton of helpful information here, in the sense that, you know, the write activity basically expands the entire pane. And it doesn't really give you any indication of, you know, which processes were doing what, and you know, which times we're truly being each process was accessing a file or something like that. And the reason for this is beyond the issue of us only capturing the bounds of first and last read and write activity, is that our shared file information is condensed down into a single file record. So as I mentioned earlier, Darshan captures per process information for each file. But if it's a shared file, then at shutdown time, Darshan will decide to condense that all down into 1 single shared file record. And what that does is, I mean, you obviously have to aggregate all these timestamps and different counters to make sense in a shared file context. And what it does is it saves us a lot of space to get rid of, you know, those redundant records kind of, but it does throw out some information, as you see here. We're not really able to tell you which processes contributed what, when for this read and write activity. So one option available to you is to just tell Darshan not to do shared file reductions. So there's this environment variable called Darshan disable shared reduction, in which case Darshan will never condense those per process file records down into a single shared file record. And you can see this is the identical example, but with the reductions turned off. And you can see, we can see the per process information here, which is a lot more helpful than what we saw on the previous screen. And again, this is not on by default. It's something that users can enable with an environment variable if they really want to kind of learn more about their shared file workloads. So it's kind of up to you whether you think this might be useful for your use cases. But we've definitely gotten some good usage out of it for understanding shared file IO. The other thing I'll mention, which I think helps out more with the question we got a couple of minutes ago, but this is a module inside Darshan called DXT, which stands for Darshan Extended Tracing. And this provides you complete detailed tracing data for Darshan's IO operations that it's tracing. So if, you know, these statistics are great, you know, in a lot of cases, but sometimes you just really want to know, you know, how each and every IO operation performed. Maybe you want to do a more in-depth, analysis of all of the IO operations that are issued, then DXT is really helpful because it captures information on every single read and write call by the application. So it'll tell you information. If you look down here at the bottom, it's kind of like a sample trace output, but it'll show you which ranks issued the operation. So rank 0 in this case, it'll tell you that it's a write. It'll tell you the exact offset and length in the file that was being accessed. You can see these are all like 1 meg accesses just sequentially through a file. And it'll tell you the start and end time of all of them. So you can kind of really dig through all this trace data to see, what are the range of response times for individual operations and things like that that aren't that may be harder to, or maybe impossible to do with Darshan's default like condensed data. So this is just a method for users to get really detailed data if it's useful for their analysis purposes. And again, this is something that's not enabled by default, just to kind of keep Darshan's memory and log storage overheads minimal, but you can easily enable it at runtime using this DXT enable IO trace environment variable. And this should work on basically all of the systems that we have Darshan deployed on that we're talking about today. And as an example of what kind of data you can use or plot with this sort of information, this is just a simple rank first time plot that shows read and write activity for an application we instrumented with DXT. And you can see the y-axis is the MPI rank and x-axis is time. And you can see just what intervals each process is spent doing reading or writing on this type of plot. This one's a little interesting in that it can show you that this application is using a clear subset IO pattern where some processes are doing IO on behalf of others, and those processes remain idle. So you can see the big gaps on the y-axis between the different processes that are actually doing stuff versus those that aren't doing any IO. So yeah, this is kind of a simple tool, but the DXT is really useful if you, like I said, really want to dig into the details of read and write activity and do some custom analysis. That's kind of the use case for that. So just as a recap, we've covered some basic usage and tips for Darshan so far today. What you want to do is each of the facilities that we've covered that have Darshan deployed tend to have their own documentation about how to use Darshan and some relevant details like where logs are stored and things like that. So it's always a good starting point for users is to have a look there to see if there's any relevant information. But some of the key takeaways are is that there are tools available today that you guys can use without any hassle on these systems. Darshan being the one we're focusing on. It can be made to instrument your application easily as is. So we saw that basically the process is making sure you have a module loaded and just recompiling your application, which isn't too cumbersome in many cases. Again, refer to our documentation and any site documentation to get your bearings with Darshan and make sure you're using it properly. And then probably the starting point for most users is almost always going to be this PDF summary generated by Darshan job summary tool. So start by generating that and then having a close look. And again, if you have questions, feel free to reach out to your support staff or us at the Darshan team. If you have particular questions, we'd be happy to help you guys out. And like I mentioned, we've got, I think we'll see Darshan on and off throughout the day. I think some of the other presentations are going to reference some Darshan information here and there. And I'll also have a deeper dive into understanding performance and tuning where I heavily rely on Darshan later this afternoon. So we'll definitely learn some more there too. The last thing I'll mention is the hands-on exercises and the repo up here at the top. There are a few different exercises that you can try tonight or whenever you have some free time. And it might be a good idea or good use cases just to get your feel with Darshan and see what the full PDF summary report like that is and see if you have any specific questions. But there's a Hello World example that we've already got one question about. This is a really simple application that does some IO that can help you test out Darshan. I think it's pretty straightforward, and that you could probably pretty easily map the Darshan output back to the source code. It's pretty reasonably easy to understand. The warp drive and fidget spinner applications are both come with like A and B versions that you can run separately and compare the performance across them. There's definitely performance discrepancies coded into these. So these are a little bit more interactive in the sense that you can compare and contrast and start to dig through the code and see if you can understand why one performs better than the other. So that would be an interesting next step after having a look at Hello World. Those last two I mentioned, warp drive and fidget spinner, will make more sense probably following Rob Latham's MPIO presentations that are coming up. But yeah, please have a look and obviously let us know if you have any questions or if you have any comments about anything. I don't know how we're doing on time necessarily, but I suppose that we got a break built in after this, so I can always take a couple of questions now if folks have any, if anything comes out from the Slack channel worth discussing quickly.
There's a question maybe you could elaborate on. We've answered some. Is does Darshan logging impose much overhead?
Right. So we really look at ourselves as being low overhead. I would say generally we like to look at ourselves as being less than like 5%, maybe a few percent, upwards of 5% of total duration of your IO calls. Which is, IO tends to be somewhat slow on these systems, so we have a lot of wiggle room before applications can really notice that we're causing any variance or anything. But and a lot of our benchmarking we've done of Darshan, it's really difficult to discern Darshan's overheads against just typical IO variability.